Okay. So now this is the last part, which is I'm not going to do the full proofs um, again, but I thought it's nice to include this uh, in the survey or the primer on quantum mechanics, which is Simon's problem. So this is basically an example of quantum advantage in the query model or the Oracle model. Okay. So what is the so query complexity is basically just saying that suppose you have black box access to a function, and given this black box access, um, so basically what that means is the only way you can access the only way you can access any information about the function is by querying the black box at different values, and you can ask, can you get an advantage in the quantum setting versus the classical setting? And Simon's problem is one very nice problem that gives you an exponential separation between quantum and classical in that, um, yeah, okay. So you need exponential queries classically. With quantum, you can do it with uh, essentially one query. Um, yeah. So it's going to be a little bit quick and a little bit hasty because um, I don't want to spend too much time on this. But here's the problem. So the problem is that you're given some function. Okay. So this is the input. Um, say given f from 0, 1, n, 0, 1, n, where f is a to the 1 function, and um, exists a string s in 0, 1, n, such that uh, f of x equals f of y if and only if x equals y, or x equals y XOR s. So this is element wise XOR, or bitwise. Okay. So this is what we are given, and the goal. So you're given this as a black box, right? So you're given this as input oracle. So you're given this as an oracle, um, and the goal is to compute. So the goal here, okay, yeah, the goal here is to um, recover S. Okay, this hidden secret S. Okay, so now if you're a deterministic classical algorithm, so this is NB. If uh, one uses a deterministic classical algorithm, um, then it's sort of clear that uh, you need at least, in the worst case, in the worst case, need at least, uh, 2 to the n by 2 queries, right? Why is that? Because it could be that every single point that you've queried just happens to be uh, such that there was no collision, right? Because it's a 2 to 1 function, so half the inputs are going to map to a different output. So it's possible that, yeah, that you had a very bad, uh, you had bad luck and you just never queried um, you never found a collision. If you don't find a collision, then you cannot learn anything about S. Okay, so deterministic doesn't work. Even if you allow randomness, so even with randomness, um, if you query much less than omega 2 to the n, uh, by essentially the same argument, uh, will not help, with high probability, but but with 2 to the, but if you make 2 to the n by 2 queries, then by the birthday paradox, you'll see a collision with high probability. Um, the algorithm can learn with high probability. Okay, so there will be a high probability of collision, and once you see the collision, then you can just recover from x and y the value of S probability. So you can find f of x equals f of y. So you find x, y such that this is the case, and then you output x, x, or y that gives you S, right? Okay. So that's what we know for the classical case. So it doesn't look like in the classical setting, you have a good chance of solving the problem without making some exponential like queries, no, exponentially scaling queries. In the quantum case, you can do the following, right? So you can start with, so here's a BQP algorithm, or basically a single query algorithm, which does the following. So you start with 0 to the n, 0 to the n, okay? And you map it to uh, an equal superposition over all inputs. This is the output register. And then you query, you run the oracle once. So you're going to get the n sum over x. And here you'll get f of x. Right? And then what you do is you measure the second register. Yes, then you'll be left with x plus, you'll be left with x0 plus x1, right? Where f of x0 will match f of x1. Okay. And now what you do is you measure these guys, the first register in the Hadamard basis. So, um, so you measure the first register now. in the Hadamard basic. And this you can check. You'll get a tool such that g dot x0, x1 is 0. Okay. And we know that v dot x0 plus x1, this is nothing but s. Right? And so you can repeat this, repeat to get a list of these, and then you can, and in order n time, you should get n minus 1 linearly independent things from which you can solve, which allow one to get S with hyperbole. That's the Simon's algorithm, and this gives you a separation in query complexity. So this mostly concludes all that I wanted to say about the basics of quantum info. And yeah, hopefully next time we can start with some more interesting quantum crypto things.